Okay, so last time, if you recall, we had looked at two of the three techniques that we had said that we will be studying. These are the advanced techniques that improve the performance of the frequency of arrival estimation problem. This frequency of arrival estimation is also sometimes referred to as spectrum sensing problem. Basically, we have a frequency spectrum that we are interested in uh, evaluating, and we want to know what parts of this frequency spectrum are occupied and what are unoccupied. And it is those unoccupied portions which we probably want to use in an opportunistic manner. This is a very pertinent problem in the context of 5G and the next generation systems, especially because, as you know, there will be a very massive uh, wireless sensor network that is being envisioned in context of 5G systems. So uh, for such uh, wireless sensing devices, uh, they, it may not be possible to allocate dedicated spectrum to each of these sensor units ahead of time because there may be just far too many such sensor nodes spread throughout, for example, industrial, some industrial farm, or if you're talking about a hospital, if you're talking about agricultural land, the number of such sensors may be massive. And so it is impractical to pre-allocate some dedicated frequency spectrum ahead of time. We may not have that large of a frequency bandwidth available. The other reason why this uh, is a problem is because these sensors may be collecting the data intermittently. You know, they uh, a lot of these sensor nodes in wireless sensor networks are battery powered, and so they uh, they may not have ability to continuously be powered on. They may be going into sleep mode occasionally. And during the sleep mode, obviously they are not collecting the data. They are not sending any data to the network. And so, in that sense, also it is impractical. It is inefficient to pre-allocate a portion of the frequency band to all these sensor units. And so now, in many of such contexts, many such scenarios, the futuristic scenarios specifically, our the problem that we are looking at becomes very relevant. A sensor node, for example, wakes up, it comes out of its sleep mode, and then it has collected some sensing data that it has to send to the central node. But it has not been given a pre-allocated frequency. And so it is at that time that it is scanning the spectrum and looking at the unoccupied portions of this wireless spectrum. Uh, and the agreement is that if it finds any portion of the spectrum which is unoccupied, it can start transmitting on that spectrum. And so a lot of the time in the literature, this problem is referred to as spectrum sensing problem. The name is different, the objective is the same. We want to determine which frequencies are present, which are active in the wireless spectrum, and which part of the spectrum uh, is unoccupied. And so in that context, we started looking at this FIR filter, the specific type of FIR filter, which is essentially a complex exponential filter. And we saw that if I just take the magnitude squared of the output of a bank of such FIR filters, which actually form the discrete Fourier transform, then effectively I am transforming the incoming signal from the time domain to the frequency domain. And then I'm just essentially getting an estimate of the power spectral density. We also looked at the mathematical formulation of the autocorrelation sequence of the incoming signal. And we saw that if we transform it, if we take Fourier transform of that, we get the ideal power spectral density, which is essentially a summation of several direct delta functions in the frequency domain. Essentially, in the ideal form of the power spectral density, we get a spike wherever there is a signal present, and everywhere else there is a noise field. And then we saw that ideal PSD, which is just a summation of many spikes, is only approximately estimated by this DFT-based filter bank. There are problems of low resolution, smearing, leakage, energy leakage, side lobes, etc. that come about. And those problems are happening essentially because each of those DFT filters are not able to completely null out or remove the frequencies which are not coincident with the actual frequency. Yes, the DFT filter will pass the actual frequency with a good strength, but unfortunately it will also register a pretty high strength at its output for a signal which is not even present. And that is coming because of that sink shape profile that the DFT filters have, which we studied mathematically, and I think which is one of the problems that you have done as a part of your lab one. Okay, so then we said that, okay, fine, we don't have to be always be stuck with that sink shape profile. We can do better. We can actually apply some windowing to the autocorrelation sequence before we take its Fourier transform. And that windowing will allow us to kind of trade off the width of the main lobe and the suppression of the side lobes. The rectangular window, which is the default window used in the DFT operation, has a specific size of the main lobe, and it has a specific suppression of the side lobe. Okay, maybe this would be a good question for you all. Who can tell me the width of the main lobe of the DFT and the suppression of the first side lobe related to the main lobe?
So 1 over n?
Yes, Pavesh, good. So the width of the main lobe is 1 over n. What is n?
The end point of the number of points for the FIR filter.
Yeah, so n is the length of the FIR filter. What is the height of the side lobe relative to the main lobe of this rectangular shaped DFT filter? Any idea?
13 dB
The 1 by
less than the
13.
main lobe.
Yeah.
Yeah, right. So Divya got it right. So it is 13 dB below the main lobe, and that the width of the main lobe is kind of in our control. We can increase n, for example, if we have that much freedom in design. We can do something with the width of the main lobe. But the width of the suppression of the side lobe is not in our control. If we decide to use the rectangular window, then no matter what the value of n is, the side lobe is going to be at 13 dB below the peak of the main lobe. And so in that context, we looked at several other windows, Hamming window, Hen window, the Kaiser window, etc., which suppress the side lobes. But it's sort of like this Heisenberg's uncertainty principle, that there is a certain limitation in what you can do. If you try to suppress the side lobes, you have to give up on the width of the main lobe. So all of these other windows that we have looked at, yeah, they allow you to suppress the side lobe, but their main lobe becomes wider than the rectangular function. So that is a trade-off that is involved in the design of the power spectrum density-based spectrum sensing design techniques. So given such limitations, we said that, okay, can we do anything better than what is possible using this simple DFT type of technique? And we looked at two different answers to that question last time. One is the music algorithm, which directly goes to the linear algebra. It actually looks at the properties of the eigenvalues and eigenvectors. And it says that if I can form an estimate of the estimate of the correlation matrix of the incoming signal, and then if I do eigenvalue decomposition on that, then what I'm going to see is a bunch of eigenvalues which are going to be smaller. And if signal to noise ratio is high, then significantly smaller compared to the other eigenvalues. And it is this small eigenvalues which tell me a lot about where the incoming signals are in frequency domain. On the face of it, this seems like we wouldn't have thought of it. I mean, even sometimes we go through an entire subject of linear algebra over one semester, sometimes two semesters, but we may not even think of this application of the eigenvalue decomposition. So on the face of it, it looks hard to believe that how can you just look at, well, first of all, why there should be a bunch of eigenvalues which are much smaller than the others, and then why should the eigenvectors corresponding to those small eigenvalues give us some information about where the frequency of arrivals are. But that is one of the properties that we have looked at, and it is indeed the case that this small eigenvalues, and specifically the eigenvectors corresponding to these small eigenvalues, all of these eigenvectors are 90 degrees from any signal vector. In this multidimensional space, it is hard to imagine how the orientation of these vectors is going to look like. But one thing we can definitely imagine is two vectors being perpendicular to each other. And the consequence of that is that each of these eigenvectors corresponding to what is known as this noise subspace, that vector is perpendicular to the incoming signal vector. And so the music algorithm actually leverages that property of EVD. It actually scans the entire frequency spectrum. And then for each frequency, it forms a dot product with all of the eigenvectors corresponding to the noise subspace. And if you are at the actual incoming signal frequency, then all of those dot products are going to become zero. And so the way the music algorithm formulates the scheme is it puts that dot product in the denominator. And so therefore, when you get zero as the dot product, the ratio is going to become infinity. Essentially, you're going to get a nice spike at the location of the incoming signal frequency. And we saw that the performance, we saw visually last time, that the music algorithm's performance is pretty dramatic improvement over this power spectrum density estimated. So that was one algorithm that we have looked at. Wanted to say something about the music algorithm. Oh, yes. Okay. So, at this phase of your MTech studies, I know all of you are doing a lot of reading doing a lot of literature survey and all that, literature search. One thing that I would like you to keep in mind is that when you read the papers, some of the papers especially, are a little difficult to read. There are some terminology and some nomenclature that is being used, which is uh, not going to be familiar to you. But it is just that uh, there are some accepted conventions which are used, which may seem like kind of very formalized manner of speaking, but that is what people do, the authors who write such papers. And so in the literature search, whenever you come across any terminology which says subspace, okay, you have to right away think that they are talking about eigenvalue decomposition. So subspace-based technique, maybe you wouldn't know what they are talking about. What is subspace-based technique? Well, whenever they talk about subspace, almost always it means that there is some concept of eigenvectors and eigen decomposition involved. And a lot of the times, this topic of subspace-based techniques end up being on this noise subspace versus signal subspace and how they are mutually orthogonal. So the music algorithm that we studied is a classical subspace-based technique. And it actually very efficiently and cleverly exploits the orthogonality between the noise subspace and the signal subspace. And it says that these two subspaces are actually mutually orthogonal and mutually non-overlapping. I mean, obviously they have to be non-overlapping because otherwise they cannot form 90-degree angle with respect to each other. And also the underlying property says that the overall dimension of the space in which the total combined signal, the actual signal of interest plus the noise, the dimensions that combined signal occupies is the summation of the dimension of the signal subspace and the dimensions of the noise subspace. So those are the some of the uh, underlying concepts that have driven the music algorithm. Oh yeah, the other thing that I wanted to mention about the music algorithm is that, in fact, it actually does away with the need of putting those uh, a, a bank of bandpass filters. You actually don't need them uh, because that equation that we had seen last time of the music algorithm, where we have some summation of dot product magnitude squared in the denominator. In fact, knowing the coefficients of the vectors forming the noise subspace, that equation can be written in a closed form. It becomes essentially a polynomial equation. And the frequencies of interest are correspond to the zeros of that polynomial equation. Okay, so an advantage of music, another advantage of music compared to the power spectral density technique is that you actually don't need that hardware. You don't even need a filter, specifically this uh, bank of FIR filters that are required for the power spectral density based estimation. All you need is a numerical equation solver. And it can actually, you just solve the root of that equation and this is solved. Hello? Hello? Yeah, go ahead. I'm doing the lecture right now, but okay, I'll call you later. Okay. And so that that is a variant of the music technique which is called root music. Basically, you are trying to determine the roots of this polynomial equation. If you can solve the polynomial equation, and now there are many good numerical solvers, you directly get the answers, the, the locations of the frequencies of interest. Okay, so the root music is a technique which actually allows you to do away with actually putting up those signal processes. Although you will have to do a lot of number crunching in the software, but you don't need corresponding hardware for that. Now, music is one technique. The other technique that we have seen last time is known as minimum variance distortionless response technique. And if you recall, there in the music, the entire focus is on linear algebra. When we go over to MVDR, we have to kind of brush up our skills in terms of taking derivatives and all. And in fact, it is not just the skills, but we need to form some basic concepts regarding the complex analysis. And you may not have taken a math course on complex analysis, so we didn't get into too much detail of what it means to say that we are taking derivative of a scalar with respect to a vector, especially when those quantities are complex values. But instead of that, we just wrote down a tabular summary of all the derivative rules that we need. And using just those rules, we were able to solve this optimization problem, which the MVDR looks at. And then the MVDR also, and actually the final solution of MVDR is also somewhat like music algorithm. In the music, we have V times V Hermitian in the denominator, where V is this matrix whose columns are the vectors of the noise subspace. Instead of that, in the MVDR, that V times V Hermitian is replaced by RXX inverse. This is what I want you to think about, that RXX inverse, the inverse of the correlation matrix, is also going to give you the same AND effect as what this VV Hermitian matrix of the music does. At the frequency of interest, at the actual incoming frequency, that quadratic term W Hermitian RXX inverse W is going to become 0. So that is what I would like you to think about. Why should it become 0 at the location of the frequency of interest? But it does. And then we get the same end effect. We get 1 divided by 0 at the location of the actual frequency. And so we get a big spike. MVDR is maybe more general than the music in the sense that music, I don't know whether it can be thought of as a filter. Maybe not the specific technique of the music, but the general underlying idea of forming the signal subspace can be thought of as a filter design solution. But the specific music algorithm, you can't make a filter out of it. Whereas MVDR, you can actually do filtering. So the MVDR in that sense is maybe a bit more general solution than the music. But I would say that music probably slightly outperforms MVDR in this spectrum sensing problem. Now there are this music algorithm and the MVDR algorithms were formulated in late 70s or maybe even late 60s. So maybe almost 40 to 50 years back. But after that, there have been many enhancements of these basic techniques. A lot of mathematicians kind of jumped into this central idea. And there is one technique called Esperit technique, which is, I'm not going to get into, but it is considered to be even more better. Performance is improved compared to the music. And then there are many variants of music which kind of slightly improve the performance of music algorithm. The MVDR technique also is kind of generalized, and we can probably formulate some similarity of MVDR technique to the more general least squares technique that we will be studying later on in this course. Okay, so that is where we were last time. Now, today I want to talk about yet another solution of this FOA estimation, which is actually which takes a completely different viewpoint. And it solves actually, it appears to solve almost a different problem. But in the process of solving this problem, it actually makes use of MVDR technique. And the reason why I want to look at this method is because I won't say that the applications of, I mean, okay, let me put it this way. The domains of application of music algorithm and the MVDR algorithm are, let's say, one or two different areas of research. This third technique that we are going to look at, it actually exposes us to a whole new domain of applications and a whole new domain of research. Whenever you talk about correlation matrices, autocorrelation sequences, whenever you talk about the eigen decomposition, etc., whenever we do this, the type of calculus that we did last time in order to derive the MVDR solution, whenever we do Lagrange multiplier technique, we are actually doing a lot of machine learning. We are kind of coming to grips with a lot of machine learning techniques, because all of these techniques are heavily utilized in the machine learning literature. This third technique that we are looking at today is actually even more closely tied to machine learning technique. This technique, the specific algorithm that we will be looking at, is called expectation maximization algorithm. And it's a very powerful algorithm. It has a very wide range of applications. And a lot of these applications come from machine learning instead of communications or signal processing. So that way, it is a very useful algorithm for us to kind of come to grips with. And the second aspect of this topic that we are going to look at is that it also relates us to the compressive sensing framework. The problem is the same. The objective remains the same. We are still trying to formulate a technique that allows us to determine the frequency of arrivals, but the approach is based on compressive sensing and based on expectation maximization. So let us jump right into it. So remember that we had looked at this model of received signal where there are k simultaneous sources and some n samples. And we had said that this is the model of the received signal, which can be put in a vectorial form. X is equal to W as U. And just for your recollection, I'll go to that particular slide where we had formulated this. This is the slide where we had first formulated the mathematical expression. I think this slide should be familiar to you all now. It has actually become a famous slide. Probably I come back to this slide over and over again. So you see here, X is equal to WS plus U. So I'm just stating that same expression here. Now here, one thing I did for the sake of notational simplicity, I removed the times index n that we had used for this vector x. Okay, and but other than that, it is exactly the same mathematical formula. What we are interested in knowing is the frequencies corresponding to the columns of this matrix W, because it is those frequencies which tell us where the incoming signals are. Okay, so now this is where the entire problem, somebody, some clever guy, kind of recast the entire problem in a very different manner. I mean, similar but a different manner. Okay? The incoming signal is still the same. The vector x is still the same. But and the vector of noise samples is also the same. But what this idea says is that instead of writing this x as w times s, I'm going to write it as a times z. Okay. Now, in this formulation, I don't know what w is. That is actually my problem statement. I want to determine the columns of w, because if I can do that, then I have solved the spectrum sensing problem. Whereas here in this formulation, this A matrix is known. The reason it is known is because we put in this A matrix all possible values of f that we can think of. Basically, f, as we know, varies from minus 0.5 to 0.5. So we just sample this frequency domain within this range as fine as we want. Suppose we take m different samples, maybe m is 1000. Then we actually are going from minus 0.5 to 0.5 in 1000 steps. And for each value of f, each value of this capital M different values, we know how to formulate the corresponding column matrix. And so now we have made this matrix A to be much bigger than W. The number of rows remains the same. N doesn't change because N is determined by the size of the problem. So we can't mess around with N. But here, this K, which is the number of incoming signals, is some value smaller than N. Now, over here, we are replacing K by capital M, where M is potentially much larger than N. And this A matrix we can calculate ahead of time. Now, obviously, if I replace this W with A, then I have to do something with this S also to get the same X. And that is where the compressive sensing technique comes into play. In this method, this S vector has been replaced by this vector Z, and the dimensions have to be necessarily m cross 1, where m is again some very large value compared to n. The idea is to say that this Z vector is mostly 0. And only few locations in this Z vector are non-zero. And exactly at those locations, Z becomes same as S. And everywhere else, Z is 0. And so those zero valued elements of Z will kind of null out the corresponding columns of A. And so what will remain in the final product, A times Z, is going to be same as W times S. Is this clear?
Yes, sir.
Okay.
Yes, sir.
Okay, good. So, so if we formulate the same problem in this alternative manner, then we can say that the frequency of arrival problem actually boils down to identifying which are the non-zero elements of Z given the measured X and given the knowledge of this matrix A. But that is essentially the compressive sensing problem. So you see that this FOA estimation technique has been recast into the compressive sensing technique. Now, from now on, well, yeah, I would say for, yeah, more or less, okay, I think there may be some departures, but more or less from now on, till we conclude this compressive sensing based approach, you can forget about this being an FOA problem. You can forget that this is a spectrum sensing problem. This can be any compressive sensing problem. And you know that compressive sensing is applicable in domains which are other than the communication domain. It is, for example, applicable in biomedical engineering. It is applicable in computer vision and so on. So in that sense, now we have kind of generalized, we have expanded the scope of the problem that we are looking at. The solution is kind of, again, going to get back to the FOA technique, but the main concept would be applicable in these other domains as well. Okay, so let us look at what we just now said in a more graphical manner. So this is the graphical way of stating the problem, where we are assuming right now that I have only one measurement vector. So I'm forming only one data vector X, and that X is represented by this column vector. This is that matrix A, and A matrix is to be thought of as a horizontal box. It's not a vertical box. It's like a thin little box sitting on the floor, rather than a tall cabinet whose base is smaller than its height. Basically, this n is smaller and in some cases much smaller than capital M. It cannot get arbitrarily smaller. For example, n cannot become smaller than k. So essentially, n has to be larger than the sparsity of this vector z. But it will be much smaller than the number of columns of this matrix A. The z is this sparse vector whose only few elements are non-zero. All the white ones are zeros. And this signal vector we are measuring in presence of some noise. So this is the schematic, the visual representation of this equation that we have seen. Now, there is not a reason to just say that I am going to tie my hands with just one measurement vector. I can actually collect multiple measurement vectors and basically form multiple columns of X. And when I do that, this A matrix is obviously not going to change, because in A I put the whole kitchen sink. I threw everything that I had in this A matrix. So that obviously doesn't need to change. But this Z vector now becomes a matrix also. A key assumption in this technique is that the sparsity of the vector Z follows onto the sparsity of this matrix capital Z. Okay, so basically the diagram looks like this. So you will see that this vectors became matrices, except when we turned the vector Z into a matrix, we said that only few rows of this Z matrix are non-zero. All the other rows are zeros. And this is not an unreasonable assumption, because if the signal is going to be sparse, then that sparsity is probably not going to vary dynamically. Essentially, if some transmitter is sending the signal, is transmitting at a particular frequency, that transmitter is going to be active over a certain number of samples. And so unless we make this capital P, which denotes the number of columns, both on the right hand side and the left hand side of this equality, unless we make capital P to be very large, we can safely assume that the sparsity is going to be a static scenario. The sparsity is not going to be dynamically changing with time. Okay, so that is the statement of the problem. Now let us look at the algorithmic solution of this problem. So we are looking at this expectation maximization algorithm. A very high level summary of this algorithm is to say that we want to estimate expected value of magnitude of Zm squared. And as we saw in the prior slides, this value will be non-zero only for those elements of the vector Z which are active. And that will directly tell us what frequencies are active. Now, the way we can restate this problem for all values of M is to say that maybe we can form the correlation matrix of Z and just look at its diagonal elements, because it will have a total of M diagonal elements exactly equal to this expected value of Zm squared. Okay, so this is the parameter of interest, which is captured in the diagonal of this RZZ matrix. Okay. So whenever we talk about an algorithm, especially if it's an iterative algorithm, which is what this EM algorithm is, we have to first state how are we initializing the algorithm. And then we have to say what we are doing inside each iteration of the algorithm. So the way this algorithm is initialized is by taking RZZ to be either randomly generated or sometimes even just an identity matrix. If you have some knowledge of what elements of Z are likely to be non-zero and what are going to be zero, then actually you can bring in that knowledge. And so that is probably one of the advantages of this EM technique, is that it allows you to kind of input some knowledge about the overall problem, which is outside of the box. Basically, the music and the MVDR and even the power spectral density techniques, they work inside the box. Even if you have some extra knowledge from which you can kind of rule out certain frequency locations, that doesn't help you in music algorithm. But here in the EM algorithm, if you have that outside of the box knowledge, you can put it to good use by more smartly initializing this RZZ. But what is quite impressive is that even if you'd say, I don't know anything and I will just take it to be a random diagonal matrix, or even not random, I will say that all of these M values are all ones, because I don't know anything other than that. Then also the algorithm works actually, which is quite surprising. See, in this formulation, we saw that there are only few rows which are non-zero. All the others are zero. In the EM algorithm, if I say at the initialization, because I don't know where these frequencies are, even if I say that all of them are present, which is quite quite something. I mean, I am saying that I will assume that all of these capital M frequency locations are present, which is a gross error, because only capital K, which is a number much smaller than capital M, is actually present. So the way I am initializing is grossly wrong. Then also this algorithm actually figures out what these frequencies are, and it does that in an iterative manner. Okay, so the next step is to look at what are the iterations, what are they doing. Okay, so inside the iteration we have this MVDR method sitting in. Just like what we did in the MVDR, inside the iterations of this EM, we form an MVDR filter for each value of f. And remember, there is total of capital M values of f in that matrix capital A. So basically, we go column by column of that matrix A, and for each column, we form the MVDR filter. Now remember, this is the expression for MVDR filter, which requires us to have an estimate of Rxx. In the original MVDR technique, this Rxx is formed using the actual observation of what X is. We get the incoming samples, and then using that we estimate X, using those incoming samples, we form the correlation matrix. Whereas here, in this technique, this RZZ is used to estimate Rxx. RZZ, along with this column vector WF, will tell us the present estimate of Rxx. And so using that estimated Rxx, we formulate the MVDR filter. And then this is simply passing the signal through the MVDR filter, where we do this on each column of capital X. Remember, we have multiple measurement vectors. So we use this MVDR filter on each of those measurement vectors. So we will get total of capital P such outputs for each value of M. Okay, so does it make sense?
Yes, sir.
Okay, so this is the first step of the EM algorithm. Now, the second step is simply to say that each of this total of capital P outputs gives me an indication of whether the signal is present or not. If the signal is absent, then hopefully this MVDR will have done its job. Although we initialize this RZZ in a pretty inaccurate manner, this MVDR will still tell me at the output, this YP of M, if a signal is not present at this location M, hopefully the magnitude of YP of M will be small. If the signal is present, hopefully the magnitude will be large. But remember, there is the noise also present, and the initialization is pretty gross. And so individual YP values may not be highly accurate. And so that is where the second step, which is known as the maximization step, comes into play. Essentially, what we do is average all of the YP values. Remember, we have a total of capital P data vectors now. And so we can run the MVDR on each of these P data vectors, the measurement vectors, MMV vectors. And for each output that we get, we average it out. And that becomes our new estimate of RZZ. We do it for all of the capital M values as we go along each column of matrix A. and that gives us the mth diagonal component of RZZ. As we complete the scan over all columns of A, we get the entire RZZ. And we are keeping it to be diagonal. And so this RZZ goes back in the next iteration. And hopefully now it will be an improved estimate of RZZ. So this is the expectation maximization algorithm. It's a watered down version of expectation maximization. The actual EM algorithm is more, it makes use of formulas which are a little more complex. But I mean, we are not in a position to kind of fully grasp the formulas. If you want to implement those formulas, you can just implement it blindly and get it going. But to understand the concept behind those formulas, we are not there yet. Later on, when we study the MMSE algorithm, we will be better able to appreciate those formulas. But otherwise, the idea, the concept, the general approach remains exactly the same. So this is the EM algorithm. Okay. Now, one thing that I think I will do now is I have one or two papers that I thought will be useful for us to look at this juncture. So let me see if I can find them. Okay, are you able to see this paper now?
Yes, sir.
Okay.
Yes, sir.
So this is a paper that makes use of the EM algorithm, and I'll put this paper on our Google Classroom. This is where it summarizes the algorithm. This is our initialization step. Remember, we said that we can initialize the RZZ either in a completely random manner, or we can even set all of the values of RZZ to be 1. So you see that is exactly this step number 1 here. This is our step number 2, where there is E step and M step. This matrix here, sigma matrix, is let us see, it is same as our re-estimated RZZ, and so that is they are saying that this is the equation for that. The first line of equation 16 is how they are re-estimating the sigma. And then, as I said, the equations look very different compared to the MVDR, but the concept remains the same. In the expectation step, the algorithm does the number crunching over equation 16. And then in the maximization step, algorithm does the number crunching over equation 18. And this equation 18, you can see, is same as our maximization step that we had, this here. Okay, you see here we are doing this averaging of the absolute value squared, which is exactly what is being done in the first term of equation 18. This 1 over L is our 1 over P, and then this summation over YPM squared magnitude is essentially this mu I norm squared. The notations are different, and so that is kind of one of the hurdles in understanding some of these papers. Going from one paper to the other, the notations can change drastically. So that can throw you off a little bit. But if you're trying to get to a particular concept, then you can kind of see through those superficial differences. Basically, this part is the same as what we just looked at. And then it has this additional sigma II term, which we don't have right now because, as I said, our EM algorithm is kind of watered down. Here, they are applying the MMSE technique. And so they have to bring in the diagonal elements of the sigma matrix also. But other than that, this algorithm, again, it using those equations 16 or 18, it updates this gamma, which is our diagonal RZZ, and then it iterates over expectation and maximization steps. So this is the EM algorithm in its full glorious detail. What I just showed you is kind of a simplified version of EM algorithm, but the main idea is fully captured. So what I will ask you to do in the next lab is to implement all of these three techniques: the music, the MVDR, and the EM. Okay. So now I will take a break. Back in just a few minutes. Oh yeah, one thing I wanted to ask you: the lab number 2. I had set the due date to be sometime last week. I think end of last week. But none of you have turned it in. Is it because you are kind of running late on lab 2 and you need more time?
Sir, Vibin sir told that he will take another lab on Tuesday regarding that lab 2 only, and then it got postponed to Thursday, so that's why we did not send it last.
Okay, so I'll then set the due date to be Thursday. Is that fine?
So Friday, because Thursday and last part, so making up the report Friday.
Okay, fine. Friday. So I'll set the due date to be Friday. Then I'll give you the next lab on Friday itself, so you can start working on it. Okay, I'll be back in just a few minutes. Okay, so I'm back. So let us continue for another maybe 20 minutes or so, and then we'll stop. I think I have already shown you this performance results for these various techniques last time. I'll just quickly go over them. Oh yeah, this EM technique, I don't think I showed you the performance for that. So very briefly, let me say what this chart is showing you. It is essentially showing you the estimate of that diagonal of RZZ. And ideally, this diagonal element should be non-zero only for the locations which are specified in the red, and everywhere else it should be zero. So basically, it should form the same type of pointed needles at each of the locations of the red. When I initialized the algorithm, I made all of this capital M values between minus 0.5 to 0.5. I made all of them to be 1. And so that is why this initialization line, which is in the blue, is 0 dB. 1 in the logarithm domain is 0. And so that is why we get this one here. But this MVDR technique actually takes even this grossly wrong RZZ and still somehow manages to figure out that maybe this parts here, there is not much of a signal present there. And at some locations which are similar to this red dots, the signal is present. So this first estimate that you see itself looks pretty good. It went directly from this flat inclined to forming the spikes exactly at the locations that we wanted. The second iteration of the EM made it even better. And then third, fourth, and fifth kept on sharpening these spikes. So this is showing the performance of this simple watered down EM algorithm that I have described to you. I haven't implemented this more detailed algorithm that I had shown in that paper. I'll ask you to do it, and hopefully, excuse me, just for a moment. So I'll ask you to in lab 3. I will ask you to implement this algorithm in the full ugly details which were provided in that paper. Okay, all right. So now this is the end of the main material on the frequency of arrival estimation. Now, the rest of the slides for today are going to be on the beamforming. We went over this entire discussion keeping in mind the time domain and frequency domain viewpoints, which is the conventional viewpoints. Now, what we are going to see is that the beamforming viewpoint actually falls immediately out of this mathematics that we have seen. So everything that we have discussed so far, we will be able to translate that earlier discussion to the beamforming problem. The reason why this beamforming topic is important is because, as you know, in the 5G systems, this MIMO and especially massive MIMO techniques are kind of leveraging this beamforming algorithms a lot. And so understanding the theoretical aspects of beamforming will allow us to appreciate the advanced MIMO techniques which are being currently investigated in the literature in the context of 5G systems. So just like the traditional FIR filters, which we can think of it as filtering the frequencies, as we saw, the FIR filters filter out some frequencies which are far away from the designed frequency of that filter. The beamformer, you can think of it as FIR filters which filter out some space, or specifically some directions in the space. Okay, so that is what this filters do. There is a simple mathematical model which is called the uniform linear array, and here these triangles represent antennas, and uniformity means all of these antennas have a uniform separation among them, and linear is because they form a line. Okay, so that is where this notation is coming. And what we are going to say is that there is some transmitter who is far away and who has transmitted some electromagnetic signal. That electromagnetic signal is again a narrowband signal. So it can be represented essentially as a complex exponential. Typically, there will be those symbol terms present here, but right now we are not looking at that. What we are saying is that this transmitter may be oriented at in certain direction in the space, and therefore, depending on the orientation of the transmitter relative to this uniform linear array, this electromagnetic wave is going to arrive at certain angle theta. And so this theta can be drawn in two different ways. Both of these are angles theta. You can easily prove it to yourself. Basically, theta is the angle that this incoming signal makes with respect to the line corresponding to this array of elements. And so the way this, so we are saying that the signal is arriving from this direction. So it is coming in like this. And so what it is going to do is, it is going to travel across this ULA. So first it was here, then after some time, it will reach the second antenna element. Then after some other time, it will reach the third antenna element, and eventually it will fly by the linear array. Because the distances are the same, the time that this wavefront takes to go from first to the second antenna is the same that it takes to go from second to the third antenna. And so that time is sometimes denoted as this tau value. Just hold on. Okay. Sorry for the interrupt. So you see that this wavefront is taking some time to go from one element to the other. How much time does it take? Let us see. The way to figure out the time is to maybe do some simple trigonometry. One way is to just tilt the array by angle theta, so this incoming wavefront becomes horizontal. So from that you can see that the distance, the extra distance that the wavefront has to travel is given by this vertical line. This vertical line makes 90 degree with respect to this solid green line, and the hypotenuse of this right angle triangle is obviously equal to d meters. And so this extra distance is obviously d times sine theta. And so the extra distance that the wavefront travels going from first element to the second element is d times sine theta, using this simple geometry. And therefore, this tau becomes d times sine theta divided by the speed of the light. Okay, so this is the formulation of tau. So let us recap our notations, our incoming signal is continuous in time. Okay, unlike the FIR filter where we had discretized this incoming signal, it was a discrete time signal. Here we are not saying that it is discrete time, it is continuous in time. So it's a function of small t, continuous time variable. But still, the expression of the signal at the output of the nth element of the antenna array takes a form which is very much similar to what we had seen in the context of discrete time domain filter. Xn of t is given by a complex exponential of 2 pi fc t minus tau n, where tau n is nothing but n times tau, because there are n such delays that have happened. And so I can obviously bring out xt outside of this exponent, and then I multiply it by w and f, and that w and f is nothing but exponent of minus, there should be a j here in front, it's a typographical mistake. So exponent of minus j 2 pi fc tau n. Okay, so it's the second term of this equation. Now the rest of this equation just simplifies tau n. So tau n is d sine theta n divided by c. So that is what I substituted here. But c divided by d is the wavelength in meters, and so instead of writing it as c divided by d, I'm just writing it as lambda. Now the units are making sense. D is in the meters, lambda is also in the meters, and so I can take the ratio, and that ratio will be a unitless scalar, and that scalar is what I'm calling capital F of D. And then I have a ratio of sine theta divided by f of d, and that is what I'm calling as small f. So with that, my expression for xn of t becomes very much like what I had for the discrete time FIR filter case. The only difference is that in that formulation, this small f was not sine theta divided by fd, but it was instead of that what it was. Can anyone tell me? How did we formulate small f earlier?
Capital F by in
Yes, capital F divided by fs. What is capital F?
the analog frequency in continuous time.
Analog frequency in hertz, and f of s is
The sampling rate.
sampling rate. So here our small f is sort of like that. And so then what we conclude is that this capital F of D is sort of like our sample rate, except this sampling is something strange. It is lambda divided by D. And this sine of theta is like capital F, but that also doesn't seem like any frequency as such, but it plays the role of frequency. And so with that, what I can say is that we will think of sine theta as our space domain frequency. And obviously the range of sine theta is -1 to 1. And we have seen earlier, I think in lab 1, that small f has to be within -0.5 to 0.5. It doesn't matter whether small f is defined as sine theta divided by fd or capital F divided by f of s. If it goes outside of this base range, then you have the ambiguities because of aliasing. And so what we want to make sure, just the way we made sure in the discrete time case that uh, capital F does not exceed half of f of s. Here we have to make sure that the sine theta divided by fd remains within this limit. So that calculation is very straightforward to do. We have to just make the maximum value of this space frequency divided by fd to be less than 1/2, which will also make sure that the minimum value of that ratio will be greater than -1. But obviously max of this sine theta is 1, so 1 divided by fd has to be less than 1/2, which means fd has to be greater than 2, which means lambda divided by d has to be greater than 2, which means that the separation between the elements has to be less than half the wavelength. So this equation here is called the space domain counterpart of the Nyquist requirement. In the traditional Nyquist requirement, the sampling rate has to be twice of the maximum frequency. Whereas in the antenna arrays, we cannot increase the separation between the antenna elements to become bigger than half the wavelength. If we do that, then we will have the same aliasing problem that we had seen in the context of time domain. Specifically, our spatial frequency will get aliased. Spatial frequency is the sine of theta. And so if sine of theta gets aliased, the only way it can happen is if theta is getting aliased. But theta is, remember, our direction of arrival. So what this equation tells us is that if this inequality is not met, then our antenna array will not be able to say whether a signal is coming from 30 degrees or, I don't know, maybe 70 degrees. Because both of those signals will look exactly the same to the antenna array. I think one of the experiments that you had performed showed that if you had some frequency 1, 8 and 9/8, if the sample rate is 1 hertz per second, sorry, 1 sample per second, 1 hertz, then 1/8 and 9/8 looks same, identical. So here in that context, if this condition is not met, then two different angles will appear to be identical. We will not be able to tell any difference. Now, that is the only difference, I would say, between the model that we had looked earlier and now this beamforming model. Otherwise, everything else pretty much applies as it is. All you have to do is make substitutions. So when in the time domain context, we were talking about frequency of arrival estimation. In the space domain, we would be saying that as, what would be the statement of our problem? It won't be FOA anymore.
It has to be angle of arrival.
It will be angle of arrival, AOA. Instead of FOA, it will become AOA, angle of arrival. Sometimes it is called direction of arrival, or DOA problem. So in the literature, these terminologies are interchangeably used, FOA, DOA versus AOA. In all such problems, the idea is to figure out this theta. But other than that, the same methodology will carry forward. So I think what I will ask you to do pretty soon is to look at those earlier slides and see whether they need to be modified. I mean, there will be some differences. Let's go over some of those differences. But you will see that the main context will remain the same. So you remember that when we started, I think pretty much in the second lecture itself, we had drawn a diagram of the tap delay line model of the FIR filters. I'm going to repeat exactly the same diagram, but now instead of representing the tap delay line filters, this diagram is going to represent the beamformer. These triangles are the antenna elements. In between two antenna elements, the signal experiences this delay T of S, which we had earlier denoted as tau. So in the time domain, this was T of S, now we are calling it tau. And the output of each of these antenna elements is getting multiplied by this filter coefficients W, which we are calling them as beamforming rates. And the beamformer just sums up all of those products and gives you the final output. So all of the slides are, you should find them very similar to the analogous slides that we have seen at the start of the semester. You see the only difference in this slide is very similar to one of the earlier slides. The only difference is that small f has become this quantity, sin theta divided by f of t. But otherwise, the rest of this part is the same. Remember, earlier on we said that we are going to take the filter weights themselves as complex exponentials. So here also we are taking the filter weights as complex exponentials. And then we said that when the incoming signal arrives at certain frequency, now it will become a spatial frequency. Then what does this filter do? In our context, what does the beamformer do? And so we will again have the exact same notation. Remember, we had this dot product representing the output of the filter. One change is that this is continuous in time. X of t is continuous in time. It has become now, it was previously discretized in time. That is one difference. But this vectors, they are looking exactly the same as before. And so what this tells us is that the output of the beamformer, which is continuous in time, is the input multiplied by a scalar. And the scalar is given by this dot product. We have already evaluated this dot product earlier. Do you remember what this dot product was? Radhika, what do you think? Are you there, Radhika? Soumya, do you remember what this dot product was? Soumya, if you're there, you can speak out. Maybe they've gone on to do some other things while keeping their laptop on. Komal, what do you think? Are you there, Komal? The question is, what was the formulation of this dot product? Anudeep? Everyone is silent. I don't know
So
if you are
sync like
All
with
identity matrix.
so we got
Yeah.
a sync
Yeah.
expression.
Yeah, sync function. Yeah, so I see that some of you respond, the others are silent. I don't know whether it is because Those other students are not even in front of the laptop, or I don't know what is going on. Anyways, so yes, it will be exactly same as what we had seen earlier, because the vectors remain the same, so the mathematics doesn't change. Okay, so this is the math remains the same, but we have to interpret now this as in context of beamforming, and the answer remains same as before. It is this summation of complex exponential terms, which we have seen earlier. It's a function of the separation f minus f naught. But again, this separation now is in terms of the angles, because f and f naught are actually angles now. They are not really, or they are actually sine of the angles. So the answer is similar to before. Basically, this analogy is telling us that when the f and f naught are similar, then we are going to get a very strong output at the output of this beamforming. And when the incoming signal's direction of arrival, theta naught, starts differing from the theta angle at which this beamformer has been designed, which defines the small f, then the output of the beamformer is going to die down. Okay, so I have just pretty much literally copied all of those earlier slides, except I made some few changes. Instead of calling it a filter, now I'm calling it beamformer. And other thing is, whenever we talk about this f or f naught, we have to remember that this is not the real frequency. It is actually denoting the sine of the angle of arrival. But it is at this point that I said that, okay, I'll let you do the rest of the slides. You can go over each slide one by one and see how, if at all, that slide has to be modified for this beamforming problem. Okay, so that is, I think, all for today. Now I'm going to get into a topic which has attracted a lot of attention recently, and that is the topic of index modulation. So we'll take up this topic in the next lecture, next Monday. Index modulation is kind of going to bring us back to the digital communication. You know, in the communication we studied, and then what we must have studied in the previous semester also. The main fundamental task was that we had a set of symbols. For BPSK, it was just 2 symbols. For QPSK 4, for 8PSK 8 symbols, and so on. And we were using some number of bits to select one of those symbols. So for BPSK, we needed just 1 bit. For QPSK 2 bits. For 8PSK, we needed 3 bits. And then we were essentially actually transmitting that symbol, and then we were letting the receiver figure out which of these multiple symbols has been selected. And so in context of 8PSK, if the receiver figures out that, okay, symbol number 4 has been selected by the transmitter, that act of figuring it out gives the receiver 3 bits of information. So that is actually the underlying concept of the modulation schemes that we had seen. The transmitter makes certain selections which the receiver is not aware of, and the receiver on its own, without any help from transmitter, and this is crucial. If the transmitter helps it out, by some indirect manner, then all bets are off. The receiver autonomously, on its own, figures out which of these 8 possibilities of 8 PSK has been selected by the transmitter. And it is this act of autonomously figuring it out is what gives the receiver 3 bits of information. Some years back, some smart researchers came up with a generalization of this idea. And that generalization goes in the context of MIMO systems. They said that the transmitter has, let's say, 16 antennas, and the receiver, let us say, again has maybe, I don't know, 8 antennas or 4 antennas, but at least more than one antenna. So what if in the most basic version of this idea, this index modulation idea, what this researcher said is that what if I don't transmit QPSK, PSK, BPSK, nothing? But all I do is at the transmitter, I select one out of those 16 antennas. Basically, I light it up. I don't activate the other 15 antennas. I just activate one antenna at a time. But which antenna I'm going to activate, it is going to be up to me. I have 16 antennas and I have incoming data, incoming bits that I need to transmit. So I'll collect 4 bits at a time. And those sequence of 4 bits is going to be all random. And so sometimes it is going to be 0, 0, 0, 0. And when it is like that, I will activate the first antenna. When it is 0, 1, 1, 1, I will activate the 7th antenna, and so on. Or actually the 8th antenna. All 0 is the first antenna, 0, 1, 1 is going to be 8th antenna, and so on. So basically, I'm going to do exactly the same thing that I would have done in 16 form. But in 16 form, using these 4 bits, I was selecting one of the 16 symbols. Whereas here, I'm not doing symbol transmission. Using these 4 bits, I'm going to select one of these 16 antennas. The physical hardware is what I'm going to select, and I'm going to emit an electromagnetic pulse through that antenna. Now, almost think of those 16 antennas as 16 light bulbs. And all of these light bulbs are switched off. And the transmitter at a time turns on the switch of only one light bulb at a time. The researchers said that what if the receiver can autonomously figure out which of these 16 light bulbs has been activated? Then, just like how it happened in the case of 16 form, the receiver will get 4 bits of information. That is the main idea behind the index modulation. We are modulating the index of the antenna. The terminology is literal. Index means actual index of the antenna. And we are transmitting the information by changing those index randomly and letting the receiver figure it out, which index is active at any given time. So that, in a very broad perspective, is the idea behind the index modulation. And that is the topic that we will briefly look at in the upcoming lecture. Now, to conclude today, what I will tell you is that at the end of this index modulation topic, I'm going to formulate a problem. And in that problem, I'm going to ask you to come up with a different type of index modulation for which the receiver will have to do direction of arrival estimation. To give you a very high level viewpoint, the idea behind this, and this is going to be your project, the first project of the semester, is that instead of activating an index of transmit array, what if I activate different directions from the transmitter? Somehow, suppose I am able to change the direction as seen by the receiver of where the signal is coming from. Can the receiver then just determine the direction of arrival? And suppose if we tell the receiver upfront that the direction of arrivals are going to be one of 16 values. It's never going to be outside of these 16 values. But I am not going to tell you what those 16 direction of arrivals are. You have to figure it out on your own, whether you use music algorithm, NVIDIA, expectation maximization, do what you can, figure out the direction of arrival. If the receiver can do that, then it will exactly get the same 4 bits of information. Does it make sense?
Yes, sir.
Yes.
Okay, so that is going to be kind of a culmination, kind of the kind of coming together of many different ideas that we have seen and putting it directly up in front of our next generation system research. Because as far as I know, this idea that I'm describing has not been mentioned in the literature. And so although I'm going to give you this as a class project, if you do a good job of solving this project, then, and we don't, I mean, I don't know. Okay, so this is some idea that I'm giving you. I don't know whether this idea is going to work out or not. Maybe when you do the simulations, you will find out that the idea doesn't work. Then also we will find out something that we don't know right now. I have not myself worked on this idea. This is just an idea that I have, which I'm going to formulate it as a project for you. So I don't know what the final answer is. So it's kind of research. When we do research, we don't know where the research is going to lead us to. But if we get something positive out of this project / research, then what I can tell you is that it will be a very strong piece of research. Because as far as I know, this idea has not been explored in the literature in that much detail. Okay, so that is where I will stop today. And I'll see you on Monday next week.
Thank you, sir.
Okay, bye.
Thank you, sir.